Hi, everyone. Thanks for tuning in. It's my great pleasure to introduce Gergely Ambrus from Rain Institute and University of Szeged. He's going to tell us about monotone subsequences in squares. Gergely, please.
Thank you very much for the invitation, and greetings from Budapest. I'm on this side of the pond. So I would like this to be like an interactive talk. So if you have any question, just stop me and then just discuss. So I'm going to talk about an old topic or a classical topic, but from a new twist. So the starting point is the longest increasing subsequences. That is now 60 years old. So it has been asked by Ulam in 1961. And I think everybody knows this question, that if we are given a random permutation, and now random permutation means that we take the uniform random element from the permutations on n numbers, then he asked what is the maximal number of elements x1, x2 up to xk, which keep the original order. So what is he called the longest increasing subsequence? So the length of a subsequence is just the number of elements. So that's what he asked. And now if we think of this question geometrically, then it is equivalent to the following problem, that let 0, 1 square, let this blue square be the unit square, and pick n uniform random points independently in this square. And now we ask the question, what is the maximal number of points for which both the x coordinates and the y coordinates form an increasing sequence? So if we order the points, for example, with respect to their x coordinates, well, with probability 1, there will be no 2 points with the same x coordinate. Then having increasing y coordinates geometrically means that this path that we obtain by connecting these consecutive points is going upwards. So it is never going down. It is a monotone path. It is a monotone path, and then we may as well add this 0, 0 and the 1, 1 vertices of the square to the sample. And we can ask for the maximal number of points, which together with these 2 fixed points form an increasing sequence geometrically. So we're gonna denote this maximal number, which is a random variable, by L1n. And n means the number of points, and 1 we will see is well, it stands for the being monotone increasing. So this problem has a long history, and the first question was like, what is the expectation? What is the order of magnitude of the expectation? And then Hammersley basically 50 years ago proved that the order of magnitude is a constant times square root of n. So that is about constant times square root of n points, which in our language, which form a monotone chain, a monotone increasing chain. And then the question, what is this constant? And independently of each other, Vershik and Karov and Logan and Shep, they proved that this constant equals 2. So the expected number of the maximal number of points in this monotone chain is 2 times square root of n. And then the question, what is the error term? Kim proved that the error term is of order n to the 1/6. And finally, in a very nice paper in 1999, Baigdeit and Johansson proved the distribution of the error from the 2 times square root n. But as far as we are concerned, it is really just the first step that we are interested in, namely that the expectation of this maximal length or maximal number of points is 2 times square root of n. And the variance is of order n to the 1/6. So this is the result that we are starting from, and we ask the following question. So geometrically, we look at these points, and they form well, a path, and this path is monotone increasing. And well, if we think of that equivalently, it means that the first derivative is positive. And the question came up: can we extend this result to convex chains? So when we don't only want this chain to be increasing from 0, 0 to 1, 1, but we also want it to be convex. So this is a question that we were studying with Imre Barány, and we had a paper in 2009. And so this is the model. Again, we can pick random points in the unit square, but because we are going only from 0, 0 to 1, 1, we really can have points only in this triangle. And now I drew not this triangle, which is half of the unit square, but just an affine, just a general triangle, because this question is affinely invariant. So we can really pick any triangle in the plane, and we pick, let's say, n over 2 points in it. And now we ask for the maximal number of points, which together with two fixed vertices, so let's say this is 0, 0, and this is 1, 1, together with these two fixed vertices, they form a convex chain. So, and we ask for the maximal number of such points, and this is what we are going to call the length of the longest convex chain. And now we're gonna denote it by L2n. So this 2 stands for the convexity, or we can also think of the second derivative being positive. And yeah, so a chain is just a set of points with increasing x coordinates. So that was the question that we studied. And so remember that the maximum number of points which form an increasing chain was 2 times square root of n. And we managed to prove that there exists some constant, so that some positive constant, so that the expected number of the maximal number of points which form a convex chain is a constant times n to the 1/3 above. So there's a nice similarity with the increasing sequences, but for increasing sequences we had constant times n to the 1/2, and here we have constant times n to the 1/3. Now the value of the constant is not known. We have some upper bounds and some lower bounds, and it seems by computer simulations, it seems that at least for, well, at least as far as we could test, it seems that this constant is close to 3. Maybe it is 3, but I wouldn't go that far. So for increasing, it was 2 times square root of n. Here, maybe it is 3 times n to the 1/3, but so this is an open question, the determination of this constant. And not only we proved that, but we also established the limit shape result, that I'm going to talk about later. So what does it mean that the limit shape is a convex curve? Well, so there is a parabola, there is actually a unique parabola, which is tangent to the sides of the triangle at these vertices, at the two ends of the convex chain. And we prove that this parabola is the limit shape of these longest convex chains in the following sense, that, well, so let's say that gamma is this parabolic arc connecting the two vertices, and the distance is, let's say, it's the maximal distance between parallel tangents of two curves. And we prove that for any positive epsilon, the probability that the distance of a longest convex chain and the parabola is greater than this fixed epsilon converges to 0. And actually, it is even true in a stronger result. So we prove the result in the form that this epsilon also goes down to 0, and still the probability goes to 0. So if we think of it like in the language of parallel neighborhoods, then with huge probability, this longest convex chain is going to be very, very close to this parabola. So that's what we mean by limit shape result. So we proved it for the convex chains. And yeah, just on a side note, so this limit shape result is not very surprising. So for example, if we take endpoints in the square and we take the collection of all the convex polygons determined by these endpoints, then there is a limit shape for those convex polygons, meaning that there is a curve, there is a convex curve, so that the probability that a uniform sample chosen from the convex polygons is closer to this convex curve than a fixed epsilon converges to 1. And it turns out that this convex curve is the maximizer of the so-called affine perimeter. And returning to the triangle, this parabola is the curve which maximizes this affine perimeter among curves connecting these two vertices within the triangle. So that's, in some sense, that's the reason why this parabola shows up, and that's the reason why this is really the limit shape of these convex polygons. So far we have two results. First result, the classical result, is for the longest increasing chains or longest monotone subsequences in random permutations, which says that the expectation of L1n is close to 2 times n square root of n. And the second is longest convex chains, which says that the expectation of the longest convex chains is a constant times n to the 1/3. And now the question is, how can we extend it further, or how can we generalize it to higher order convexity? Because, well, if one is very, very optimistic, then one might see a pattern starting here, but of course one needs to be super optimistic for that. So question, how can we extend it to higher order convexity? And first of all, it is not clear what higher order convexity means. So when we have a bunch of points which form an increasing sequence or point sequence, then we can think of these points as lying on a graph of a function, so that the first derivative of that function is positive, or that it's not negative. And similarly, when we have a bunch of points which form a convex chain, then we can think of these points as being on a graph, so of a function whose second derivative is non-negative, which is convex. And one can proceed along, or one could proceed along that line and ask for the maximal number of points which are on a graph of a k times differentiable function f, whose k derivative is non-negative. So that would be one possibility. Second possibility would be, for example, that, well, for example, if we have a convex curve, then it intersects any line in at most 2 points. So it would be possible to extend, or it may be possible to extend the definition so that these points are, let's say, k convex if they lie on a curve, so which has at most k intersection points with any line. So that is also a possibility. And then one may study all these questions. And the question, I mean, the real problem is that which definition is the good definition or the correct one. I mean, there is no such a thing, but which definition will lead to some problem that we can really study. And I was quite lucky with that, because actually there's a problem by Elias and Matuszek from 2013, and they were sort of facing the same problem. But their goal was to extend the Erdős-Szekeres theorem to higher order convexity. And it turns out that the definition that worked for them is the following. So they define K convexity or K monotonicity in the following way, that for any k plus 1 points, so p1 up to pk plus 1, they define them to be positive if they lie on the graph of a function whose k derivative is non-negative, I mean, which is k times differentiable, and the k derivative is non-negative. So, okay, so for monotone, we see that it's nice increasing function. For convex, we see it's a nice convex function. And now for general k, we can ask the same thing. So it is essentially the definition that we came up here in the second point. But there is a subtle difference and very important difference, namely that here we only define the positivity of a k plus 1 tuple. So not all the points, but just a k plus 1 tuple in the first step. And then in the second step, we say that, well, a chain is called monotone, k monotone, if any k plus 1 tuple satisfies this condition. So for example, in the case k equals 3, this is such a point set, 5 points. Any 4 points lies on the graph of function whose k derivative is non-negative. And now one can say, well, let's stop. If we are in the k equals 1 case, then, well, any 2 points, they are on a graph of such a function, meaning that this line segment connecting any 2 points is having positive slope. But then we know that all the points are on a graph of a function with non-negative first derivative. And similarly, if we know that if, for example, we consider n points in the plane, and any 3 of them are in convex position, then all of them can be written on a curve which has non-negative second derivative. So what's the reason for coming up with this definition? Is it really necessary to formulate it in such a complicated way? Why can't we just require that all the points lie on the graph of function which is k times differentiable and the k derivative is non-negative? And the reason, as it turns out, is that it really works for k equals 1 and 2, but for higher values of k, it may not work. So here, different k plus 1 tuples may be testified by different functions. And it is not necessarily true that there is one function whose k derivative is non-negative everywhere. And there are examples for that. Günther Rothe gave some example for k being at least 3. So k for k equals 1 and 2, it is true that one can just write all the points on a function, on a graph of a function whose k derivative is non-negative, but for k being at least 3, this breaks down. So that's the reason why this definition is so complicated, at least seemingly complicated. Now, there is an equivalent way for defining positivity of the k plus 1 tuple, and that uses divided differences. And these divided differences, they are really ancient. It is really an ancient notion, and then these are the coefficients in Newton's interpolating polynomial, and these are defined recursively. So for 1 point, we just define its 0th divided difference by this formula, and then given a bunch of points, we define the jth divided difference using the j minus first divided differences. And the nice fact is that k plus 1 tuple is positive if and only if its kth divided difference is non-negative. And on the other hand, if they lie on a function of a k times differentiable function, then on the graph of a k times differentiable function, then this k divided difference equals the kth derivative of that function in some point in between, divided by k factorial. So this is an alternate way of defining this positivity, and it is very useful because one can actually calculate these divided differences and work with it. So it gives the possibility for algebraic computations or working with algebraic polynomials, really. Okay, so this positivity, so we defined that the chain is positive if and only if every k plus one tuple is positive. And now actually there's a very useful fact or lemma, which says that a chain is positive if and only if every consecutive k plus one points form a positive k plus one tuple. So that is important because one can really just concentrate on these intervals among the points instead of taking every possible k plus one tuple. So again, this is something very useful when one like to check this k convexity. And then, well, we didn't define these divided differences for multisets, but then it's possible to extend it in that case as well. And there is one important thing here. So if we are given a point, then it is possible to, and we take that point, let's say I plus one times, then it is possible to define its divided difference or its positivity. But one has to specify one more thing, namely, we have to say that, well, this point lies on a graph of a function. And then depending on this function, it can be a positive k plus one tuple or not. So it is not sufficient just to take one point, but in some sense, we have to take the point and its derivatives. Okay. So boundary conditions. So for the, I mean, in order for the problem to make sense, somehow we have to introduce some boundary conditions. So we remember that for the increasing sequences, we wanted to take points in the square, and then we wanted to have an increasing sequence basically from 0, 0 to 1, 1. So our boundary conditions were just specified by 2 points. Now, when we are looking for a convex chain, then it is not sufficient just to specify the first point and the last point, but also we want to specify the sort of minimal tangent at the beginning and sort of the end tangent at the end, the last tangent at the end. So I mean, so that's what means that we are in the triangle. So the sides of the triangle define these tangents lines, and then similarly to that, when we are studying k convexity, then we would like to have some boundary conditions at the beginning and at the end. So let's say at 0 and let's say at 1. And these will be specified in the following form. We take a special curve, the graph of the function x to the k, and then we denote this gamma k x will be just this point on this curve. So it will be always the point x to the k. And now our conditions, boundary conditions, basically say that, well, the first derivative here at 0 should be at least as large as the first derivative of that function. The second derivative should be at least as large as the second derivative of that function, and so on, all the way up to the kth derivative. So in some sense, we have a condition on the point itself, we have a condition on the first tangent, and we have a condition on the second derivative, and so on, all the way up to the kth derivative. And now this is the definition that we come up with, that, well, if we choose n independent uniform random points in the unit square, then what is the maximal number of them which form a k monotone chain? Namely, they satisfy these boundary conditions and they form a k monotone chain. So let L and K be that random variable. So we have met ln1 and ln2 before. And the question, what will be the expectation or the order of magnitude of the expectation of this L and K? And then here is the main result. That, well, the pattern continues. So for L and 1, the order of magnitude was alpha times square root of n. For L and 2, it was some constant times n to the 1/3. And it turns out, and it's yeah, a really beautiful fact, it turns out that the expectation of ln k will be a constant times n to the 1 over k plus 1. So this 1/3, 1/2, 1/3 sequence continues 1/4, 1/5, and so on. But on the other hand, the exact value of this constant is only known in the case of the longest increasing subsequences. So we have some, or I have some estimates for alpha k, but in general, the exact value of alpha k is not known. And given the fact that already for the simplest case, the longest increasing subsequences, the determination of the exact constant took quite some time, namely the determination of this 2 times the square root of n. Well, we will see, but I'm not super optimistic in the sense that most probably these constants will never be known. Who knows? Maybe there's some nice idea, but I'm not super optimistic about that. Now, besides the expectation, there is also a strong concentration result, which says that these random variables are strongly concentrated. And here we have an interval of the order of magnitude n to the 1 over 2 times k plus 1. And now if we remember back for the longest increasing subsequences, it was n to the 1 over 6. That was the correct order of magnitude, whereas here we only have n to the 1 over 4. So this is not sharp, and it is not sharp also for higher values of k. So at least what the computational evidence suggests. But it is not surprising that this estimate is not sharp, because as we will see, we applied Talagrand's concentration inequality, and that is in this instance is not sharp either. But nevertheless, it does give us an exponential concentration about the expectation. All right, so these are the first two, and then after that we will also talk a bit about the limit shape. All right, so let's try to understand a bit the geometry of these k monotone chains. And the first term here is k monotone cells. So if you remember, we had these gamma ka and gamma kb. These were these 2 points on our limit shape, or its curve. And so for k equals 1, this limit shape is just a line, and for k equals 2, it was a parabola. And well, for higher values of k, we don't actually know that this is the limit shape. And now let's just ask the simplest question. So if we just look for one point which satisfies these boundary conditions, namely that together with the two multi-sets here at the beginning and at the end, it forms a convex, a k monotone chain. Then what is the possible locations for this point? All right, so for k equals 1, what is the question? Well, we have a first point, and then we have a second point. And the question, what is the set of points which form, along with these two, which form an increasing chain? Well, we know that the x coordinate must be in between these two x coordinates, and on the other hand, the y coordinate must be in between these two y coordinates. So we see that this sought after set is just a rectangle, and any point in this rectangle forms an increasing chain along with these 2 points. For k equals 2, the situation is a bit more different, very a bit more complicated. But again, then we have tangent directions. So we have a first point along with the tangency direction, and we have a second point along with this direction. And now the question, what is the set of points which along with these 2 points and 2 tangent lines form a convex chain? And we immediately see that it will be the set of this triangle. Okay, so if we pick any point in this triangle, then it forms the convex chain. So question, what is going to happen for higher values of k? And this is the truth. So for higher values of of K, we will have again some plane region. And now the plane region will be bounded by polynomials whose degree is K minus 1. And well, it will be 4 polynomials which bound this cell. We are going to call it a cell. And the truth is that any point in this cell, well, the cell is exactly the location of points which together with these points, well, multi sets of points and these sort of tangential directions form a K monotone chain. And now these polynomials, they depend, of course, not only on these points, but also this sort of fixed lower derivatives at these endpoints. And the very nice property is that the area of this cell, it can be calculated, and the area of this cell turns out to be proportional to b minus a to the k plus 1. And actually, this is the reason why this expectation is going to be of the order of magnitude n to the 1 over k plus 1. So this is just a really a beautiful phenomenon that such a simple formula is obtained for the area of these cells. And this is really this is what makes the whole approach work. All right, so these cells will be denoted by CKAB. So it means that it's a cell between endpoints gamma KA and gamma KB. So remember that these were just the points A to the K, and B to the K. Now, of course, you can say that we are cheating, because why do we consider this? Why do we consider this curve? It could be anything, but it will turn out that we will move from the uniform model to the Poisson model, and then it really doesn't matter like where exactly we are in the plane. And on the other hand, this curve is just, well, basically this is the curve that is going to serve our needs. And all right, so this is the general sort of philosophy behind the proof and what is going on. So this is this curve, this gamma k, and this is our task to find many points which, along with the first and the last points, form a K monotone chain. So satisfy all these criteria. And the question, how do we find them? And at least in order to give a lower bound, this is what we do. That we take this curve, we take the graph next to the K, and then we take a bunch of points on them. Let's call them reference points or skeleton points. And we take the cells that are determined by these points. And so here, well, we don't only take these reference points, but we take k copies of them along with the derivative specified by this x to the k function. And the reason for doing so is that in this case, if we have a K monotone chain in this cell, and another one in this cell, and another one in this cell, then the nice property is that we can concatenate these chains, and we will get a convex K monotone chain going from here to there. So this is analogous to the very simple property of the increasing chains, namely that if we have one increasing chain and another increasing chain with a common point in the middle, then we can just concatenate these two, and we get a long increasing chain from the first point to the last point. So somehow we would like to use a similar property for the higher order monotonicity, and this is how it's done, or it can be done. And okay, so once we have this property, then the next step is to drop the uniform. Okay, so far we were working in this uniform model. So we have a unit square, we have n uniform random points, and now we are looking for the longest K monotone chain, and we're gonna drop that, and we move to the Poisson model. So we will take a Poisson process of rate 1 on the plane, and we ask for, well, essentially the maximal number of points in this Poisson model, which form a K monotone chain. And the nice property is that in that case, the little events which happen in these little cells, the cells are disjoint, they will be independent from each other. So that's the reason why we have to move from the uniform to the Poisson, because in the uniform model, well, we know that there is some fixed number of points here, then of course it will affect the distribution in another one. And we don't like that. So the Poisson model works better. All right, and now we can give an upper bound in the Poisson model. So this is the method that we use, that we pick a couple of fixed points, and then so if we are given we pick a couple of fixed points, and then we sort of study these cells independently, and we study the longest k-monotone chains in these cells independently. And we have seen that the area of these cells is proportional to the differences in the x coordinates, so this b minus a to the power of k plus 1. So that means that if we have too many points, I mean too many reference points, then these cells are too small. This b minus a to the k plus 1 would be too small, and there would be no points basically inside these cells. So essentially what we want is this b minus a to the k plus 1 should be like a constant, because in that case we have like a constant number of points in each of the cells. Okay, so if we have the Poisson model, we have a Poisson process of rate one of the plane, and then we can introduce this LKP AB. So this is just the same question as before, but with the points coming from the Poisson model and not from the uniform model. And well, it has to be proven, but well, the distribution of LKAB depends solely on b minus a. So for that, one has to define a nice correspondence between two of such cells. And the other nice thing that has to be proven is that the Poisson and uniform models are sufficiently close to each other. So if we prove the expectation for one, then actually the result or the estimate will just transfer over to the other one, to the uniform model. But this all can be done, so one can really work with the Poisson model, and this is not so. This is a standard tool that is used in many instances. So here is the main result for the Poisson model, and so this LPK0n. This means the maximal number of points between 0, 0, and n to the k, which form this k-monotone sequence. And the theorem states that this is approximately a constant times n. And on the other hand, because we have this, well, you remember then this cell between 0 and n, it had the area about n to the k plus 1. So the expected number of points in this region will be about n to the k plus 1. So when we move back to the uniform model, then instead of n, we have to write n to the 1 over k plus 1 here. And that is exactly the thing that we want to prove. So there are a lot of technical details, but the core of the proof is the subadditive ergodic theorem, which states the following: that we are given a family of random variables indexed by two natural numbers, n and m, and they satisfy the following properties. Then the first property is crucial, and it is subadditivity. So it's sort of a triangle inequality. So if we have three indices L, M, and N in this order, then XLN is at most as large as XLM plus XMN. Okay, the second is shift invariance. So if we have any number S, then if we shift the process by the random variables by that one, then we get the same distribution as before. And the third is that, well, the expectation of the absolute value should be finite, and most importantly, and for us, this is the point where a lot of, I mean, when one really has to work, there is a lower linear bound on the expectation of x0. So if the family satisfies these three conditions, then there is some constant gamma, so that the expectation of x0n is about this constant times n. And so this is what we are going to apply. And of course, it's not a big surprise that what is that we are going to apply for. Let x and m be the -1 times the maximal length of a k-monoton chain in this cell between gamma kn and gamma kn. And so this is what we are going to use. And so one has to check, well, there are really just two things that one has to work on. First, the subadditivity, and second is this linear bound. So the subadditivity, it just follows from the concatenation of chains, and that is why we use this model. So if we have a convex chain here, and I mean a k-monoton chain here and a k-monoton chain there, then we can just take the union, and the union will be a k-monoton chain going from this point to that point. And then one gets the subadditivity property. So that's why these derivatives are prescribed in these endpoints. And the linear upper bound, again, it is not very complicated, but it's a bit technical. One has to prove this lemma that the expected maximal number of points from 0 to n, which form a k-monoton chain, is bounded from above by a constant times n. So it cannot be too many. And yeah, so the reason is that assume that we have a lot of points, and let's just take every whatever 10th point or every 100th point, then in between we have typically 100 points in this chain. But if there are too many of them, then it turns out that these cells, the area of these cells in which there is 100 points from our Poisson ensemble, these are just too small, and they just, I mean, there are just not enough points, not even k-monoton position, but in general there are just not too many points. So that's the philosophy behind this argument. Okay, and so one, if one gets these two properties, then one may apply the subadditive theorem, and one gets the result for first for the Poisson ensemble, and then from the uniform model. The concentration estimate goes over basically without problem. So this is the theorem, or this is the estimate. So it gives concentration in an interval of the order of magnitude n to the 1/2k plus 1. And this is just a straightforward application of Talgrand's inequality. This inequality, he has quite a number of inequalities. So this is how it reads. Assume that we have a random variable in a product probability space, and assume it is one Lipschitz with respect to the Hamming distance. So now our random variable is going to be the k-monoton, I mean the length of the longest k-monoton chain, and of course it is one Lipschitz with respect to the Hamming distance, because if we change one point, then the maximal number of points can be changed by one as well. And now this is the important condition. Assume that this y is sort of f, it is so-called f certifiable. So now what does it mean? It means that for every point x in our product space and every b bound, so that the function value of the random variable at that point is at least b, then there exists some index set with not too many elements, so at most f of b elements, so that the random variable is at least b on any point which agrees with x on that index set. So now, if we are here in this situation, well, it seems like this theorem is really designed for us, because of course, what is this special index set? Well, we have the maximal number of points in k-monoton position, and then we just fix them. So this f of b will be just b. So we just fix these points, And now we can change all the other points. These points, they stay in K monotone position. So definitely the length of the longest K monotone sequence cannot decrease. It might go up, but it cannot go down. And that is exactly what Talagram requires. And now, if this is satisfied, then we have the exponential concentration estimate. Well, about the median, but then of course the median is very close to the expectation and to the mean, and then we get a strong concentration about the mean as well. So this theorem really beautifully applies in this case, and then straightforward application gives us the exponential concentration about the mean. All right, and so now the last point is the limit shape. And so the limit shape, so Talagram basically gives us a stochastic concentration. So it proves that this random variable is strongly concentrated about its mean. And now the limit shape result basically means that we can somehow turn this stochastic concentration into geometric concentration, namely a geometric concentration. So a concentration of the locations of these longest convex chains. So the stochastic concentration is talking about the random variable, the length of these convex, K monotone chains, and the geometric concentration talks about the location of these K monotone chains. And now the limit shape result, at the moment, it only works for K equals 1 and 2 because the technical difficulties come up with for higher values of K. We will see in a sec. So let's see for K equals 1 when we have the increasing chains. So what is the argument? The argument is that, well, assume, so somehow we would like to prove that the longest increasing chain or longest monotone chain cannot have points which are very far away from the diagonal. The limit shape is going to be the diagonal, and we somehow want to prove that there are no points which are far from this diagonal. Well, assume on the contrary that this point xy is far from the diagonal. And now, well, it is a member of a longest convex chain, longest monotone chain. So a bunch of points, these green points, so that along with 0, 0 and 1, 1, they form an increasing chain. So as we are going along this path, the slope is never negative. Well, then this point xy cuts the chain into two parts, namely the part from 0, 0 until to xy, and from xy to 1, 1. And because of our because of the observation earlier, the first part of the chain is in this rectangle, in this lower left rectangle, and the second part of the chain is in this other rectangle. Now we know by affine independence that the maximal length in this rectangle is proportional to the, well, it is proportional to the square root of the points. But on the other hand, the number of points is proportional to the area. So the maximal length from 0, 0 to xy is basically proportional to square root of xy, because xy is the area. On the other hand, the area of this rectangle is 1 minus x times 1 minus y. So the maximal length here is proportional to square root of 1 minus x times 1 minus y. So this total length is proportional to 2 times square root of xy plus square root of 1 minus x times 1 minus y. Moreover, there's a strong concentration result. So it really tells us that the actual values of these small random variables are not much different from these. But on the other hand, we also have a strong concentration here from 0, 0 to 1, 1, which tells us that the probability that this longest increasing chain has small length, or just a few points, is exponentially small. And now here is the crucial geometric inequality, which tells us, well, that this quantity, the square root of x times y plus square root of 1 minus x times 1 minus y, is the largest when this point xy is on this diagonal. And moreover, we have a stability estimate, and the stability is, well, one way of formulating it is that we have a stability in terms of y minus x squared. And now this y minus x squared we see as we go away from the diagonal, it gets larger and larger. So we have some error here. And then because of that, this geometric estimate will lead to an error in the random variable. So it will lead to an error in L1n. But on the other hand, we know that the probability for a large error is exponentially small. And that turns here in the geometric language to the fact that the probability of a longest convex chain going too far away from the diagonal is exponentially small. So of course the details have to work out, but this is how it works. And now the nice thing is that for k equals 2, we again have a geometric inequality. And now our situation is a bit more different because we don't only take care of the 2 points, but we have 2 points plus 2 tangents. And also here in the middle, we have a point and we have a tangent. So this is the geometric inequality that if we have A, B, C, these 3 points, and then these 2 tangents are given, they are tangents to gamma, but at C, this line is variable, then the cubic root of the areas of these triangles is maximal. I mean, the sum of these cubic roots is maximal if and only if this point is on the curve gamma and the line is tangent to gamma. And on the other hand, again, we have a quantitative estimate on the error. So we have sort of a stability version of this inequality. And now, the same way as before, this leads to a geometric concentration. And so now what is missing in the higher values of k is basically the analog of this geometric inequality. The complication is caused by the fact that now these are not going to be triangles or rectangles, but these will be bounded by polynomials of degree k minus 1, and you have to maximize, and then you have to take the sum of these. I mean, you have to take the k plus first root of such polynomials, and then you have to take the sum of them, and you have to maximize them. And yeah, it just gets like very, very, very nasty. So I couldn't handle it for k equals 3. But nevertheless, I believe that the same approach should work, and then this gamma k should be the limit shape for k monotone chains for every k at least 1. Okay, and so now I just finished with a couple of questions. First question: can we determine the exact asymptotics, determine the value of this constant sum alpha k? Now I mentioned this affine perimeter, which shows up a lot in stochastic geometry. Can we somehow extend it to higher values of k for k monotone chains? Similarly, instead of convex halves, can we consider k monotone halves? Do those results for convex halves, or at least some of them, extend to this k monotone? Now we see that, for example, the Adler-Sekeres theorem generalizes to this k convex setting by the result of Matesek and Elias. And yeah, in general, is it possible to extend the results about random convex sets to random k monotone sets? So there are a lot of questions here, and of course also in higher dimensions and so on. So I think, yeah, there are plenty of place for further work. So thank you very much for your attention.
Thank you, Gergely. Are there any questions?
May I ask one question? Thanks for the great talk. I'm just wondering, the reason it's difficult to find this constant ck, is it because in ergodic theorem you get some constant which you don't, or is it because of that, or is it because it's difficult to calculate the precisely areas of the cells?
No, I mean the areas can be precisely calculated, so there is no problem with that. But this is so if one wants to use this ergodic theory proof, then it doesn't specify the constant. And also, well, in case of the increasing subsequences, basically I mean there are different proofs, but one really had to understand or give a sort of an alternate model or an alternate proof, which gives you the absolute value. I mean, the exact value of the constant. So there is this nice nice sort of intuition. There is this paper by Aldous and Diakonis, and they describe a nice intuition about like why this constant is 2. But yeah, it is very far from being trivial. So here, yeah, the problem is that this approach, like whichever constant works, it is not going to be helpful for that.
Is it known that the constant is the same in the Poisson and the uniform model?
Yeah, that goes over. Yeah.
Mm-hmm. That's just the approximate. Okay.
Yeah. So actually this intuitive proof for the 2, it also follows from the Poisson model, and it's sort of like a dynamical proof that yeah. So you okay. So on one hand you you are taking these points in the square, and then what you do is that you start lifting a line from the x-axis up to the y = 1 axis, and at each position of the line you take the points where your function jumps. I mean, your function is what is the maximum number of points from 0, 0 to this point, which are in increasing position, and yeah, and then on one hand you somehow see it as a particle process on the line, and then you understand something about it, but on the other hand you also think of this dynamical process when you sort of lift your line up, and sort of this duality, yeah, helps you to determine this constant. But yes, unfortunately this approach just completely breaks down already for the convex chains. So, and for this K monotone, I think it is hopeless. Maybe for the convex, still something can be done, but for K monotone, yeah, good question.